So there's a few more advanced topics that we think would be of interest, but instead of going through these in detail and depths for each one, we're going to kind of have a power segment here,
Mm-hmm.
quickly going through all the advanced things you need to know in Swift, in very quick succession. So,
Mm-hmm. Yeah.
yeah.
Yeah, and I guess the goal of this is that so if you see any of these, you can sort of know what they're called and be able to look them up further. Like it'll provide you with reference, and so you won't be completely surprised and lost by some crazy syntax.
All right, let's do it.
All right, so beginning, first things, classes. So we've had basic classes, right, so far, like our number class and stuff.
Yeah.
But we haven't talked about inheritance and overriding. So, of course, we can do that. And we can override a class. So if we want like a super number, and instead of creating our own number from scratch, UIK already includes a class, and you can have your like an NS number. And the syntax here is to use this colon, and it means that you are now a subclass of this class. And with that, you can override functions. So number has, and there's an override keyword, and you can check which, say we want to override get value, and you can provide your own implementation. And on your subclass, your implementation will be called instead of the superclasses. And within here, it's good practice. And if you can call the super implementation of get value like this. And so basically what this did is nothing. You overrode it and then called its original implementation, and you get nothing.
Okay.
Yeah. And the next thing about classes is extensions. So instead of overriding NS number, say we just want to add some extra functionality to it. And we want this functionality to be available to all NS numbers. So if you subclassed it, then you would have to use super number, right? And you might have code that already uses NS number. What you can do is actually you can extend any class you want, including your own. So we can extend NS number and add a function, super cool getter. And you can implement it as 5. And this is really powerful. So if you now have a NS number that n equals, which is a class you did not define. This is a system class.
Right.
You can actually call the super cool getter on it, and it'll actually give you 5. And this is really useful. And you can do this for your own class as well. You can extend your own classes, and now NS number doesn't have this method anymore. Yeah.
Okay, so two topics is one is a subclass that you can actually take a class you already have defined and you make a subclass for it, and that allows you to make a slightly altered version. And also you can actually extend classes. So and that if a class has already been declared, you can extend certain parameters by adding new functions or even variables to it.
All right. So the next topic, which flows nicely off of this one, is protocols. So you can define a protocol, which you can think of as sort of an interface to a class. Say we want to create a series of objects that can all be that they can all dance. So we can create a danceable object, a protocol called danceable, and what that means is, and then you can define a function called dance. And notice I didn't implement it, right? Why is that? It's a protocol which defines a way that classes can be danceable. So now I can have a class called person, and it can conform to a protocol. So if this person is danceable, it'll give me an error. Why? What's wrong with person? It doesn't conform to it. Why? Because it doesn't implement dance. To be a danceable person, you got to be able to dance. So now you have to implement dance, and as long as you have it, the error will go away. So the syntax is similar to subclassing, and you can also subclass. So if person was an NS number, which doesn't make sense, you can be a subclass of NS number, but also conform to the protocol danceable, and you can conform to other protocols as well. Like there's an NS object protocol. For example, this is a bad example. You would never want to do this. But for example, you can conform to multiple protocols. And this is going to be a very common thing you see in a delegate pattern. But when you define a protocol, basically you're defining a type of thing that can dance, and any class can conform to danceable. You can even make NS number danceable through an extension, and make NS number in the extension conform to danceable. And now you have to define dance here, and now even NS numbers can dance. That's pretty neat.
My first question is going through my head is again, by now everyone should clearly detect a Jack type example, whether it's flying pigs or people dancing. It's very very unique examples. Second thing is, okay, why protocol? Why are protocols useful? If you're just simply saying that it must have these functions, what is the situation when that's of use?
Yeah, so this allows you to make your code very much more separated. It allows you to say you made a class called like dance floor, and you don't care what's on the dance floor. You just want them to be danceable. So you would welcome NS numbers who are danceable to your dance floor. You can welcome the people and like cats and dogs, the idea is that it makes it very, instead of. So the other way you could also achieve this without protocols is if everything subclassed from a danceable object, right? But you can see how that would cause your object graph to be very weird, and it would be impossible for NS number to dance. And so protocols provide a huge amount of convenience and actually more power, functionality, to allow you to express that I just want, and notice, since you don't have to implement it, it's also very cool. So if I created the dance floor object, and it just took a array of danceable stuff, I don't care what it does. I'm not going to call anything else on it. I'm just going to call dance when they need to dance. And I trust the compiler will enforce that anything that's danceable will have dance implemented. And it's another way of doing subclassing without subclassing. It uses composition. So say in your dancing app, you have danceable people who can also sing. And now you have like singables and danceables. And you can have a class that does both sings and dances, and a class that only sings and a class that only dances. Compared to if you were trying to do this using subclassing, it would either get very messy or not work at all. And this is sort of a clean way using composition to create classes using protocols.
Okay, and we'll provide links so you can explore these in more detail, but let's move on. What else?
All right, moving on. Another type. So we talked about classes and structs. There's also enums. And so your typical enum might look like this. Types of veggies. And you have a case of carrots. And you have a case of tomatoes. And this will define, I don't think you need that. And this will create sort of enumeration of carrots and tomatoes. And you can expect that, it defines a type. Usually, you can give it a sort of a value. And in many languages, it's only can be an integer. And you can assign it to like 0, and you expect tomatoes to be 1. And in the rest of your program, you can use carrots and tomatoes as names for 0 and 1, which is very useful. In Swift, it's much more powerful. For example, it can be a string. You can have enum of strings, and you can give them. You don't even have to give them names. And you can like celery, and you can actually they will be assigned to strings of the same name, and this is very cool. So you can have a like a carrot equals types of veggies dot carrots, and this gives you a type of veggie, but you can print out its raw value like this, and it will give you its name. And this is really powerful. What it allows you to do is make your program very safe. Say you had a function that took in eat veggies, and it could take in a string, right? Like veggie. But if you eat any arbitrary string, you might die. Like what if they pass in like lead, right? That would be terrible. You don't want to eat like rocks and other stuff. But if we instead make it a type of veggie, now you're safe because you have defined that you can only take these kinds of veggies. And in this function, you can only get carrots, tomatoes, celery, and you're happy and even healthy.
Interesting. How would you call eat veggies right now? Would you call it by passing a string or?
You could. So enums are a type. So I defined a type called type of veggie. So I would have to pass in a type of veggie. But you can either do a dot, and you can choose between the existing ones, like that, which basically passes into case, or you can sort of create your own like random veggie and initialize it because it is a type, and you can initialize with a raw value called carrots, and actually create a type of veggies object with carrots. And if you do something like evil now, like you want to feed him lead, it'll give you nil because it is not a valid type of veggie, and so you're very much protected from eating bad veggies. Yeah, so Swift has a lot more sort of enums are much more powerful than they are. I mean, I even just shown here, they can even have parameters, and that's a really crazy concept that you might not ever use, but just to know that it exists, and you can see references on details. Yeah.
What else?
So continuing down, we talked about structs, classes, and enums, which are all sort of classes. They all define types, and they all have initializers. And up to now, we've used them. Say let's bring back our classic car with cup holders with cups class, and if it has a cup holder, it needs an initializer to, when you create it, to assign all its values, right? So just this, and we've seen this many times now. Just this class with a car with cups, I'll just call it car. A car with cup holders will not compile because there's no way to initialize cup holder when you're creating the class. And so Swift, as a very safe language, will not allow you to create a car where its cup holder is unsure, like it's not initialized. Like I don't know if it has a cup holder, like who's going to buy that car? So you have to specify a initializer using this format. You can do one of two things. So the first thing you can do is you can initialize it. You can always have a default initializer called like two holder. It's a brand of cup holder. When you do this, Swift actually creates a default initializer for you, so you can now instantiate a car. And with this default initializer, we'll just set up all the default values. And if you don't have default values, it won't work because it doesn't know what to do. You can't instantiate a car without cup holders. So the next thing you can do is take an initializer. Define a custom initializer that takes a cup holder in and assigns it. And note that Swift will keep complaining, even if I have an initializer, but I haven't initialized anything. Because there's no point of having an initializer the point is to initialize all your properties. So if I put this back in, Swift will be happy. And now I can create my car, not like this though. Now I must pass in the cup holder. Cool. And that's sort of initializers. And then there's different, on top of this, there's different types of initializers. This becomes a required initializer because, I mean, it's the only one, so it's required. You can't initialize in any other way. Now we can also have a convenience initializer, which is, as its name suggests, for convenience. So, I mean, there can be a convenience sort of empty initializer that sets it up to be and a convenience initializer has to call a required initializer to complete it. It's only for convenience, so it would have to call cup holder with some sort of cool cup holder string. And what this allows you to do is now create a new car directly with the convenience initializer, which then calls the required initializer and now gives you a car. And with the convenience initializer, you can do, I mean, this example, we've exhausted this example a bit.
Yeah, but how do you know which initializer you're calling?
Here I'm not passing in anything, and that matches.
Just by the arguments you're passing.
Yes,
right?
so because this initializer has this argument, and so it's always calling this one will always be calling this one, which in turn is called this one. Yeah.
So you, based on that, you could not have required and convenience initializers that had the same argument set.
Yes.
Otherwise, you wouldn't know which way.
Yes, otherwise they're basically defining the same method twice, because again, the function is defined by its types, right? So you would be redefining the same function. So yeah, so the idea here, I mean, one last thing here is if car was a subclass of a string for some reason, now I would have some errors because you have to call your superclass's initializer always, to make sure that after your class is done initializing, the superclass has a chance to initialize too, right? Or else, even though you've initialized your things, you can't. The superclass hasn't got a chance to initialize its own variables. So so every required method must call its superclasses initializer, required initializer, and every convenience initializer must call your own initializer. So it's sort of hierarchy of how you can initialize classes. And this is a very big topic. And again, there are readings that you can see to drill down into it. And the very last thing is sort of de-initializers, which is the opposite of initializers, but you only get one. And whenever, this is basically called whenever your car is deallocated. And in here you can do extra cleanup-y things. It's basically like dealloc in other languages.
Yeah. Cool. Great. So in these advanced topics, is there anything else that we should cover? Or?
We're basically through. We've for the last few, these are incredibly advanced, and I would call them expert topics. And we might not, but they are good to see.
Maybe we can just allude to them and then provide links for everyone to then review, so we don't have to write the code for these examples.
Yeah, sure. So there's some Swift supports generics, which are supported in some languages. And this is very important. Why don't we still write something? So because an example of this in the system is sort of an array. As mentioned, arrays are strongly typed, which means you can have an array of int, an array of string, and such. In each of those are types. So if you were to write Swift without generics, you would have to define every single type of every single array, right? You would have to define the int array and the char array and everything. But with generics, you can, if you look at an array, sort of, if you look at the array class, hopefully we can look at it, it's actually defined with these angle brackets, which makes it a generic, and it names the generic type a element. So whatever you pass into the angle brackets, it automatically, it creates an array of that type for you. So all you need to define is an array using generics, and you automatically get int arrays, char arrays, any sort of arrays you want, which is really powerful and important, but something that you may not ever use in your own app. And so just to touch upon that here, another thing is operator functions. Swift supports operator overloading and even defining custom operators, which is very cool, and which means that you can change the meaning of any operator. You can override, say, the plus for a certain class. And this is very useful. Say you had your own class that defines vegetables, and then if you have now two vegetables and you want to add them together, I mean, what does that mean, right? Like, do you cook them? Do you chop them up? Do you mush them in a bag? You can overload this plus function to do anything you want. So you can define what it means to add a vegetable to a vegetable. And maybe it means you stew them together, but you can define that inside the. You can define it, and even cooler is that's sort of overloading an existing operator, the plus, right? You can define your own operators, like you can find this cool knife operator on a vegetable to cut it, and you can call it like cut, and then you can now do this and like your vegetable, like a carrot, and you can define what this does. It's sort of like, so an example is -1. What is the negative sign? It's an operator that operates on 1 that negates it. And so if you define sort of this cool knife on a on a veggie, you can write the function that this calls and give it and call it this operator that cuts the veggie.
It's interesting.
Yeah. It's very interesting, and then, again, something that you have to be very cautious of. With great power comes great responsibility. And if you wrote a crazy operator that looked like this, no one else will know what that means, and you have to be very careful in your code to avoid writing things that no one will ever know what they mean. Yes.
Some of these advanced topics we might see as we go to the more further on in the courses, but for right now, the point was just to provide an overview for the audience of what some of the, if you see things that may not make sense, we just wanted to make sure that some of the basic ideas were covered in Swift.